Okay, so for this lecture, we'll be starting from where we finished in the last class. That is, we were near at the end of chapter 9, application of DFT, and this was the last topic that was remaining, convolution via the frequency domain. So for today's lecture, we'll be covering this, and then the first few topics of chapter 10, that is Fourier transform properties. So let us start. So the last topic that was remaining from application of DFT, that is the convolution via frequency domain. The main idea of this is that we have already said that due to the duality principle, duality property among time domain and frequency domain, anytime we want to perform convolution in the time domain, we can do the equivalent operation by performing a multiplication of operation in the frequency domain. And know that multiplication is a lot easier than convolution, because convolution is multiplication a lot of times and then a lot of additions, which follows a particular looping structure. But normal vector multiplication is very easy because it is just point-to-point multiplication, which can be easily handled by any kind of special libraries that handle vector and matrix products. So for this reason, the main topic here, the main idea here is to convert the task of convolution into multiplication. So the it starts off with this scenario that probably somebody somehow despises convolution, or probably it is mainly because it is very tedious and complex to carry out. So suppose you despise convolution, so you want to make it so that you don't have to do convolution. In that case, what you could do is you could just transform the two signals that you would want to convolute. You can transform them into the frequency domain, then multiply them point by point, and then transform the result back into the time domain. So the whole procedure is basically replacing one convolution with two DFTs. That means a forward DFT, a multiplication, then an two DFTs. That is performing DFT of two signals, then performing a multiplication operation, and then one inverse DFT. So it seems like in order to perform convolution, you're doing too much work, right? Doing DFT itself is quite difficult if you think about the complexity. Convolution is big of n square. Actually, not big of n square, is big of nm, where n is. So let us think that in the worst case, convolution would be big of nm, where n is the number of samples in x and m is the number of samples in h. So assuming that both of them are of the same size, it would be big of n square. Okay, if n and m are equal, then it would be big of n square in the worst case. Also, what we are trying to do is we are transforming it into the frequency domain and then doing those things and then transforming back. So that's also big of n square. That is, DFT, inverse DFT themselves are big of n square. Then how is it better? So that is what we are going to be discussing here, that how this is better than doing convolution. Even though they seem to be on the same scale of complexity, still why are we saying that convolution in the frequency domain using multiplication is better? So this is what is being said here, that is convolution bad enough that we'll have to go through all this trouble? Yes, and the thing is, there are two reasons why we are avoiding convolution and going through all this trouble. The first is that convolution is itself mathematically difficult to deal with. Just as I said, in the worst case, it can be big of n square if both the input and the impulse response are large enough. And another thing is the problem of deconvolution. In other words, the inverse convolution. Those of you, I think both of the groups have already completed this particular lab where I gave them the task of finding the inverse convolution function. So that is a bit difficult. Direct convolution has its own looping structure, but inverse convolution is a bit difficult because you have to backtrack, and there is no clear-cut way of doing this. You have to write a lot of if-else functions maybe, and write some loops which and within it you'll have to write a lot of if-else functions. So deconvolution itself is a very difficult task to do for any kind of implementation. But if you think of it in terms of multiplication, that is in the frequency domain, this becomes easy, because in the frequency domain, if you wanted to perform inverse convolution, all you had to do was just perform a division operation. Since you are multiplying to perform convolution, the inverse convolution function would be simply a division operation, right? So it seems that the in the frequency domain, the inverse convolution function becomes very easy to design, because you are not actually designing any inverse convolution function. You are just performing a division operation, which is the inverse of multiplication. So this is one reason. That is, when you are trying to find x, when you normally, what we have is, we have x, we have h, and we are trying to find y. Now if y is given and h is given, how do you perform the inverse convolution to get back x? So that is a bit difficult to design. You can design it, but you'll have to do a lot of work. So, and it is actually very difficult for a huge signal, if the output was a huge signal, because most of the time obviously y is a lot bigger than x, both x and h, because its size is n plus m minus 1. So if both of them are huge, y will also be huge, and from that huge signal, getting back x is a highly complex task. Even if you design the loop, it will take a long time to compute. So for that, uh, the other way of getting back x would be to simply calculate capital Y, to calculate capital H, and then perform a division operation in the frequency domain to get back capital X, and then you perform inverse DFT to get back X. So this is easier than designing than going through the inverse convolution function. So this is one of the reasons why uh, performing convolution or for deconvolution in the frequency domain is easier. Another reason why we want to avoid convolution is the computation speed. That is the standard convolution algorithm that we know, that is both the input side algorithm and the output side algorithm. Both of them are slow because of the large number of multiplications and addition operations that must be done. So also DFT is also slow, as we have said. The normal DFT that we know of, that is also slow. So still, why are we saying that going through the frequency domain would be better? That is mainly because of this, the fast Fourier transform. The recent breakthroughs in this field, that is the newer version of DFT, that is the fast Fourier transform. This one is a lot faster than DFT. Here we did not discuss about the fast Fourier transform, but I can still tell you the complexity of fast Fourier transform, why it is less than DFT. For now, just know that it is big O of n log n. Okay. Remember that I talked about how fast Fourier transform converts DFT into a lot of DFTs by performing a kind of interlaced decomposition. So a lot of DFTs of small length. So that is why ultimately the complexity of fast Fourier transform becomes n log n, whereas DFT would be n square, big of n square. So this is obviously smaller than big of n square. So that is why the fast Fourier transform allows you to very quickly go towards the through the frequency domain and also go back from the frequency domain. The inverse fast Fourier transform is also there. So this one allows you to move back and forth from the frequency domain very fast, and doing a simple multiplication operation in the frequency domain is simply a big of one operation. Even if you think that you are multiplying n samples for n samples together, but still any kind of library that handles vector multiplication can do it in almost big of one time. So ultimately the whole procedure becomes big of n log n to go to the frequency domain. Then you perform a multiplication. Suppose that is big of 1, simple vector multiplication, and then you convert back to the frequency from the frequency domain to the time domain. So that is also big of n log n. Okay, so the ultimate thing is, the whole thing is big of n log n. So this becomes a lot faster than just doing convolution, which is big of n square in the worst case. So that is why we want to go through all this trouble that we just said. So that is why they are saying that performing convolution in the frequency domain is better than performing convolution in the time domain. And here, when you're doing convolution in the frequency domain, you're actually doing multiplication. So now what we said is that you will be doing multiplication in the frequency domain. So how would you do multiplication for complex numbers? We have said that in the frequency domain, you have complex numbers, right? RE and IM, or else if you just consider a single capital X array, that array holds complex numbers, something like 1 plus 2i. If you do not want to store separate REX and IMX, then you would have something like this, 1 plus 2i, then something plus something I. In this way, you'll be having a lot of complex values. So how are you going to multiply complex numbers. So we already know from our intermediate level mathematics how complex numbers get multiplied. In the polar notation, this is easy, but in the rectangular notation, it's a bit tougher. So in the polar notation, what we have is when you multiply two complex number x and h to get y, what you would get is in the polar notation, the magnitude of y would be simply found using the product of the magnitudes of x and f. So magnitude y equals magnitude x times magnitude h, and the corresponding phases would get added. So this is how multiplication of complex numbers in the uh, frequency domain will happen, in the polar notation will happen. So in the polar notation, magnitude equals magnitude times magnitude, and the phase equals phase plus phase when you're performing multiplication of two numbers. And otherwise, if you want to perform uh, the same multiplication using rectangular notation, that means where the rectangular notation is re plus I im, that means you have a real component plus I times imaginary component. When you have something like this, in that case the corresponding rey would be rex times reh minus imx times imh, and the imaginary component of y would be imx times reh plus rex times imh. You can actually go through the derivation if you want, but the ultimate result will be this. It is easier to remember this than go through the derivation every time. But if you want to find the derivation, then simply remember what you're doing is just try to do this multiplication and see what you get. Try to derive it and see what you get. You would get something like x1 x2 plus I times something, and when you go through all of these derivation, finally you would get something like this, where x1 x2 are the real parts. So see that the real parts are getting multiplied, and the part where you have the imaginary, those will get multiplied also, and that is how you would get the real part. The whole real part would be here, and plus the imaginary part would have something like this. You can actually go through the derivation and see what happens. So ultimately the expanded version of it will be something like this, and this is actually a bit harder than remembering this. This is easier if you want to do it in the polar notation. Also, what we said is if you want to perform the deconvolution, suppose you're trying to find out h or x from y. Suppose you have y and you have x and you're trying to find out h. What was the impulse response that gave you this? In that case, what you could do is you could just simply perform a division and you would get h, and then convert it to the uh, time domain and you would get the impulse response, right? So in that case, we are talking about the division. So how do you perform the division in the complex for complex numbers? So this is how you would do the division. In that case, the magnitude would get divided and the phase would get subtracted. Okay, so this is just the inverse operation of multiplication, as we have said. And in the polar notation, this would be a bit more difficult. So this is what you would get in the polar notation. Okay, and it is easier to just remember this than go through the derivation every time. Instead of remembering this, it is you can actually go through this method. That means converting to the polar notation and then doing this, just simple division and subtraction of phase. This is easier. Okay, so now that we can perform multiplication and division of complex numbers, both in the polar notation and the rectangular notation. So now there is also another problem we did not address yet. So there is the convolution of an endpoint signal with an endpoint impulse response results in an n plus m minus 1 point output signal. So if you remember, x has length n and h okay, in the smaller. Okay, so in the time domain, x is length n, h is length m. So y would have n plus m minus 1 length, right, in the time domain. But in the frequency domain, what we have is when we're multiplying an n signal with an m signal, what do we get? So we are not performing convolution. Here we are directly performing point-to-point multiplication. So can we do this? Can we perform multiplication of n point with m point? We cannot. We can only do this when we increase m to make it equal to n by padding. We can only multiply equal length signals. So if m is not equal to n, then we cannot perform point-to-point multiplication. In that case, we'll have to pad it with zeros until it becomes equal to n. When it becomes equal to n, then we can multiply it. So if you multiply an n times signal with an n times signal, if you multiply it now, we would get an n point signal. Okay, so an n point signal with an n point signal getting multiplied will give you a n point signal. We are not getting n plus m minus 1. So this would create some problems. Okay, so this particular problem is being discussed now. So notice that here this was the input signal, this was the impulse response. Originally it was up to this, it was defined up to this, but then it got padded by zeros until it became equal to this. So now when you perform convolution of them, you would get something like this. Okay, notice that you can actually think of in the frequency domain, the result would be getting distorted a bit. So that particular thing is getting discussed here. Now consider in the more general case that the input signal is 256 points long, while the impulse response contains 51 non-zero points. Okay, this makes the convolution of the two signals 306 samples long. Okay, so if this is 51 non-zero points, rest are zero, so we had to pad it. So now just think of it in the time domain. What would have happened if this was 51 points and this was 256 points? If you perform convolution, n plus m minus 1 would give you a 306 samples long y, as shown in C. Okay, so this is C. So this one contains n plus m minus 1 length signal using the normal convolution algorithm that we follow, either input side or output side. Now the problem is in the frequency domain, we are performing multiplication, right? So there are only 256 samples allowed in the output signal. So if you did this in the using multiplication instead of performing normal convolution, if you did this using multiplication in the frequency domain, you would not get 306 samples. You would be allowed 256 samples at most, because you're padding it to make it equal to this. So if you multiply them point by point, you can get at best 256 points. So what are the extra samples, where are they going? Okay, so this one will cause one problem. Okay, so the 256 points end up being a distorted version of the correct signal. So the correct signal would have been 306 samples long, but now you're getting 256 points sample. So these 256 points would become a distorted version of the 306 points. So this problem is called circular convolution. And in order to understand circular convolution, we have to remember that an endpoint DFT views the time domain as being an infinitely long periodic signal with n samples per period. Okay, so this in the frequency domain, we can think that this is not the whole signal. We can think of it being repeated. Okay, so we can duplicate it and repeat it to the left and to the right infinitely, right? So if you do that, you'd get something like this in all of the. So this is just one snapshot. You can have this repeated to the right and left also. So for just this part, we can think that if you repeat it to the left and also repeat it to the right, you'll see that the first few samples of itself will get distorted by the last few samples of itself. Okay, so the last few samples, that means after 255, 306 minus 255, I don't exactly know how many samples that would be. 256, 306 minus 250, so how much would that be? 50. So the last 50 samples. Okay, so the last 50 samples and the first 50 samples of itself would get distorted. Okay, as you can see here, the first 50 samples would get distorted by the last 50 samples of itself, and also the last 50 samples would get distorted by the first 50 samples of itself. Okay, so this problem is known as circular convolution, because since in the frequency domain we can view it as being infinitely repeated to the left and right. So some of the samples of itself would get distorted. By distorted, I mean they would point by point add up, and this is not the actual uh, signal that we will get in this part. Since they will add up, it will be something like this, and also here it would be something like this. It would be something that would not be its actual value. Okay, so this particular phenomenon is known as circular convolution. And notice that you can actually go through this particular thing, and it actually explains all those things that I just said. So now what is the solution for this? Once we know the nature of the circular convolution, it is actually quite easy to avoid. what we have to do is we simply have to pad each of the signals being convolved with enough zeros to allow the n plus m minus 1 points. So here what we were doing, here this was the largest signal, so we were padding only this one with enough zeros to make it equal to this. But now what we have to do is we have to pad this one as well. We have to pad this one with enough zeros and also this one with enough zeros to make their length equal to n plus m minus 1. So if this is 51 points and this is 256 points, so the total number of points here would be 306, right? So we'll have to add zeros here after 256. We'll have to add zeros here so that it becomes equal to 256 306 samples, and also we'll have to add extra zeros here in order to make it equal to 306 samples. Only then we can have, instead of truncating it up to this, we will have the whole thing here up to 306. Okay, when we perform multiplication in the frequency domain. And then if we repeat it to the left and right, we won't be getting any extra any distortions, because when we are repeating, we are starting from here, we are not starting from here and distorting it. Okay, so this is how we get rid of the circular convolution problem, just padding enough zeros to make it equivalent to n plus m minus 1. So this is what is said here, how we get rid of this. And now we also come to the theoretical aspect of why we are calling it circular convolution. So if we look back at this figure, that is 99D, uh, this one. So if you look at this, so I've already said why we are calling it circular convolution, but so now let's just clear it out in terms of theory. So if we examine that, we'll see that all of the periods are the same. So the same signal is getting repeated to the left and right. We are taking one period of it and repeating it to the left and right. And anytime we go to the right and we do not find any more signals to, any more samples to give, we just start from the left part and we add it here. Okay, so we are ending one period here, so the next part would come from here, and the left part, the left most sample of it would start from here again. Okay, so this is what it says here. And so the whole thing can be considered as a single the whole frequency domain can actually be considered as a ring or a snake biting its own tail. Okay, so as if the whole endpoint time domain behaves as if it were circular. So the thing is, the whole thing can be considered as if this point is connected to this point. Okay, so this point is connected to this point. The whole frequency domain can be thought of as being connected like this. So as if you take this point and you connect it to this point, that is, the whole thing can be considered as a ring. If you think of it as a ring, so as a single circle, so the all the amplitudes here are just getting drawn over this ring. No matter how big your period is, always the whole period can be thought of as one single ring, uh, where the starting point and the ending point are the same. So this starting point and the ending point are the same. By same I mean wherever the ending point ends, the starting point begins right after that. Okay, so this is how you can think of the whole frequency domain. That is why we are calling this circular convolution. Okay, so that wraps it up for the chapter application of DFT. And like I said, the rest part of this lecture will cover the first few topics of chapter 10. So we'll start with chapter 10, which is Fourier transform properties. So this chapter particularly talks about the different properties. Like we said, for convolution was linear. It had these properties we already said. So here we'll also be talking about what are the properties that Fourier transform, what are the properties that are applicable for Fourier transform. So whether it is linear or not, whether it maintains linearity or time invariance, shift invariance, all these things. So let us start. The first thing that was okay. So the first thing is that it was shown in the previous chapter that convolution in time domain is equivalent to multiplying the corresponding frequency spectra. Okay, so now we will be talking about the other mathematical operations such as addition, scaling, and shifting, because they also will have some kind of corresponding operations in the frequency domain. So are they the same in the frequency domain, or do they have some kind of different dual counterpart? So here first we talk about linearity. the Fourier transform is a linear operation. To put it simply, it has both homogeneity and additivity property. And in case you guys forgot what homogeneity and additivity means, homogeneity means that a change in the amplitude in one domain produces an identical change in the amplitude in the other domain. So in terms of function, homogeneity would be something like this. F of ax would be a times f of x. And here, if we are saying that if this f is the Fourier transform function, that is the DFT function, then the DFT function follows this property. That is, if you scale the argument that you're passing to the function, the signal that you're passing to the function, if you scale it up, then the corresponding it would be equivalent to scaling the result of the DFT. Okay, so passing a scaled up version of the signal is equivalent to scaling the result of the DFT. So this is what it says. If the frequency domain is represented in a rectangular notation, there is kx. In that case, kx would be equivalent to multiplying each of the real and imaginary parts getting multiplied by k. Okay, if the frequency domain is represented in polar notation, in other words, in that case, k would not get directly multiplied to each of the x values, because you have two things here now. There is magnitude and phase. In that case, only the magnitudes would get multiplied by k, while the phase would remain unchanged. Okay, so the basic thing is that in the frequency domain, you have capital X. So if you're multiplying it with k, what we mean when we show the homogeneity property is that you're actually multiplying k with both the real part of x, and also multiplying k with the imaginary part of x in the rectangular notation. But if you follow the polar notation, what would happen is you're multiplying k with only the magnitude of x, but leaving the phase as it is. Okay, so the phase of x would be as it is. So the different representations of real complex numbers is that one is by real and imaginary number, and the other is by magnitude and phase. The magnitude and phase actually decouples the information, the intensity information from the angular information. The angular information is not affected by any kind of scaling. Only the amplitudes get scaled. Okay, but in the rectangular notation, it's a mixture, almost like RGB. So if you guys remember from the previous from any kind of graphics or graphics course, or from image processing, you guys did not have image processing, so you guys maybe don't know about this. So the basic thing is that in case of images, we can represent images using RGB, a combination of RGB, or by simply HSI. So in HSI, we have separate components. Okay, so HSI decouples the color information. So this one represents the color, this one represents saturation, and this one represents intensity. So you can actually separate out the different components, but here you cannot separate them out because the combined effect of them gives one color. So this is similar to the combined effect of two components, and here we are separating them out, the amplitude information from the phase information. Okay, so that is why k will only affect the magnitude, not the phase. Also, now let us go to the additivity property. What would happen in case of additivity? So additivity says that a function would be linear. So the additivity property means that a linear function would allow, if you add two signals, if you add two parameters and then send them to the function, this is equivalent to adding the result of two parameters themselves. Okay, so if you add if you pass these two parameters separately to the function and then add them, this is equivalent to just passing the addition of them to the function. This is what the additivity says. And here we are saying that DFT is that kind of function which follows this property. That means DFT, if you pass an addition of two signals to DFT, this would be equivalent to adding the result of two DFTs. Okay, so this is what basically additivity means. Okay, so this is what actually says here. Now here we are saying that this is not just a and b, both a and b are complex numbers, right? So we are passing two values to DFT. Suppose we are passing a plus b to DFT. Now the thing is that a plus b are not just normal numbers, these are complex numbers. In that case, what would happen? How would we show the additivity property in this case? So in this case, we could show it like this. It shows that the additivity property means that the real parts would be uh, adding the real parts would be equivalent to getting the DFT of the real part, taking the DFT and only the real part of the result, and also separately the imaginary part would follow the same procedure. That means A plus B, here A has RE and IM, B also has RE plus IM. So you can think of it in this way, that taking the DFT of two results, of two sums is equivalent to taking the real parts, taking the summation of the real parts, that would be equivalent to the result of the real part of the result, and taking the summation of the imaginary parts would be equivalent to the imaginary part of the result. Okay, so this one is in the rectangular notation. So what would happen in the polar notation? In the polar notation, you can think of it in, okay. So here, I did not, okay, in polar form, it cannot be directly added. Okay, I forgot to mark this. So in the polar form, in the rectangular form, it is easy to see that you can just add the corresponding real parts and imaginary parts. But in the polar form, the spectra cannot be directly added. They must be converted to the rectangular notation, added, and then reconverted back using the formulas that we already know. Okay, because this is a bit difficult to add due to some other reasons that are actually discussed here. That is, two signals in the polar form only get added, two amplitudes in the polar form only get added when their corresponding phases are equal. When the phases are equal, then they get added. Okay, the amplitudes will add. So addition is a bit difficult. When you add two signal values in the polar notation, they get added when their phases are equal. But when their phases are opposite, then instead they get subtracted. Okay, so this is the reason why normally polar notation cannot handle addition, because the things are dependent on the phase. So instead, it is easier to simply perform it in the rectangular notation form, and then you convert it back into the uh, polar notation if you want to keep the whole thing in polar form. Okay, so next we move on to, okay, before we move on to characteristics of the phase, there is one thing remaining. That is, in spite of being linear, we have to remember that Fourier transform is not shift invariant. So linearity means that we have the homogeneity property and additivity property. But remember that Fourier transform does not have the shift invariance property. Okay, that means shifting the time domain signal does not correspond to a shift in the frequency domain. And this is why we are going to talk about the characteristics of the phase now. Okay, so in the mathematical form, we have xn can be converted into the polar form like this, magnitude x and magnitude phase x. Now shifting the time domain signal results in xn plus s, okay, or xn minus s, whatever. If you perform right shift, then it would be xn minus s. Whatever you do, the thing is that the magnitude would not change. In the polar notation, only the phase would change. Okay, so here one thing to remember is that adding two signals, adding two complex numbers is easy in the rectangular form, and on the other hand, shifting is easier in the polar form. Notice that in case of shifting, only the phase changes, magnitude does not change. But if you were to think about in case of the real and imaginary part, it is difficult to find what would happen if you shift the time domain signal. If you perform a shifting in the time domain part, the corresponding both the real and imaginary parts would change, and that would be unpredictable. It's not directly following in kind of formula for now. We'll be coming to that later on, but know that it is easier to do it in the polar form. See that in case of the polar form, only the phase would change. That is what we know. The magnitude would not change. So it is easier to work with shifting in the polar form. Okay, so notice that in figure 10.3, the time domain waveform is symmetrical around the vertical axis. Okay, so in 10.3, so this is the figure that they are talking about. So figure 10.3. So we'll be using this figure for showing some examples now. So pay attention to this particular figure from here on. So the time domain waveform, it is symmetrical around the vertical axis. And for such type of symmetrical signals, we would have a linear phase in the frequency domain. and this was actually explained in chapter 7, if you remember. And by linear phase, it okay, we'll be coming to that later on in chapter 7. What we discuss, we'll be talking about that a bit. So now, what are we saying? Why are we saying that it is symmetrical? So the thing is, you can actually think of its shape. The time domain signal can be thought of as symmetrical because its shape is uh, the same from left and right. Okay, no matter how you shift it, its shape is symmetrical, right? If you shift it to the suppose this is the original one, focused at 0, at the center, the middle, n by 2, and if you shift it to the left, you get something like this. If you shift it to the right, you get something like this. And the thing is, in all cases, the phase is linear. So one thing to remember is that for any kind of symmetrical signals, symmetrical time domain signals, the corresponding frequency domain representation, in the frequency domain polar representation, you would see that the phase is linear. Whether it is a straight line, uh, straight horizontal line, or a straight positive slope line or a negative slope line, that actually depends on the shift. Okay, so if it is left shifted, it would be a positive slope linear phase. If it's right shifted, then it would be a negative slope linear phase. And if it is symmetrical right on n by 2, then it would be a simply horizontal line. Okay, so we'll be coming to that later on. How are we getting this straight line towards the positive slope? How are we getting the straight line towards the negative slope? So that one will actually come from here now. So if you remember from last part of chapter 7, where we discussed about the polar nuisances, if you remember that part, the pi 2 pi ambiguity and the pi ambiguity, that is where these things were already discussed. Okay, so if the signals do not have left and right symmetry, they would have non-linear phase. We'll be coming to that later on. So now figures E and H show the phase of the signals in A through D. Okay, so from A, B, C, D, all these signals have their corresponding phases shown in E, F, G, and H respectively. Okay. And as described in chapter 7, as I have said, the phase signals are unwrapped. Okay, so you might be thinking that how are we getting the phase to be a single straight line? So this is actually the unwrapped version that we talked about in last part of chapter 7. Remember that in chapter 7, something like this was discussed, that from pi to minus pi, we can have phases from pi to minus pi. Okay, so we can have phases from pi to minus pi. One might see that the phases are defined in such a way that it cannot be from greater than pi. Okay, so whenever it becomes greater than pi, we start from minus, it gets started at minus pi again, and then goes up to pi, then gets started at minus pi again, then goes up to pi. So we showed something like this in the last part of chapter 7, if you remember. So now they also said something like, this is because how we are implementing the phase to be never greater than pi, or never smaller than minus pi. But even though all the multiples of pi can be taken, but we do not take it in that way. So what we could do, in other words, is that if we unwrap them, that means we connect them end to end. That means this point, if it is connected here, then if this point is connected here, so if we join them like that, then this would be something, a positive slope phase, right? So that is what is being shown here, a positive. This is the unwrapped version, and this was the wrapped version originally. This was the wrapped version that was shown in the last part of chapter 7. Okay, similarly, this one is also obtained in that same manner. Okay, so this was all. If you want to get a refresher on this, you can go to the last part of chapter 7 in polar nuisances and check out the discontinuities part. There is the 2 pi ambiguity and pi ambiguity part was discussed there. Okay, so now we can move on to the next part. That is, when the time domain is shifted to the right, uh, the phase remains a straight line but experiences a decrease in slope. So this one is what is being shown here. If this is a horizontal line slope, so now we'll be talking about how we know that this is a horizontal line slope. That we will come to that later. For now, remember that if it is right shifted, the slope would get decreased. So this is how we get this one. Note, for now, just assume that for such a kind of signal, symmetric signal, we would get a horizontal line slope, horizontal line phase. Now, if we right shift it, we get a decrease in slope. If we left shift it, we get an increase in slope. Okay. So now the question is, how do we know that we would get a horizontal line slope for such a signal? Okay, so the figures B and F display a unique case where the phase is entirely zero. Okay, B and F, that means B is the corresponding time domain signal and F is the corresponding frequency domain phase. Here we are only showing the phase, not the magnitude. So notice that uh, here we are seeing that just it's a zero phase, a horizontal line phase. So how are we getting this? This will happen when the time domain signal is symmetrical around sample zero. So now the question is, how is it symmetrical around sample zero? It seems that it is symmetrical around sample n by 2, right? It is symmetrical around n by 2. So if this is n, this is n by 2, it seems that it is symmetrical around n by 2. Why are we saying that it is symmetrical around 0? So the phase that here we are saying that the phase is 0 because it is symmetrical around sample 0. That is because the reason it is symmetrical around sample 0 is because mainly we can think of it in the frequency domain. We can think of it in this way, that it is it can be repeated to the left and right equally, right? Just you can take this period and repeat it to the left. So this point in the frequency domain, this point would be connected to this point. So all the samples before it would come here. So you would get the same uh, shape here as well. So if you get this same shape here, you can think that for the zeroth sample, it will see the same signal to the left and also the same signal to the right. So that is why this whole signal is actually symmetrical around sample zero. In other words, you can actually say that any signal that is symmetrical around sample zero would also be symmetrical around n by 2. Or in other words, any signal that is symmetrical around n by 2 uh, is also symmetrical around 0. So this is the basic takeaway. And any signal that is symmetrical around 0 in the corresponding frequency domain phase, it would have 0 phase. It would be a horizontal line at 0. Okay, so this is what is said here, that at first glance the symmetry may not be obvious. It may appear that the symmetry is the signal is symmetrical around sample 256, that means n by 2. But remember that DFT views the time domain as circular. In the corresponding frequency domain, this it would see it as circular. So it would have sample 0 inherently connected to sample n minus 1, the last sample. So any signal that is symmetrical around sample 0 will also be symmetrical around sample n by 2 and vice versa. Okay, so now figures D and H show something of a riddle. The last one, this one, shows something of a riddle because this one shows multiple phases. Uh, this one was actually D can actually be obtained from B. If you think about B, B had 0 phase. So D, how can D also have 0 phase, then negative phase and positive slope phase? Now we'll be coming to that now. So imagine that D was formed by shifting the waveform C slightly more to the right. So C was already shifted right from B. Okay, so B can be shifted right and you can obtain C. Now if you shift C a bit more to the right, what would happen? This sample, this particular part of this particular part would be here. So, and this part, since there is no more samples to the right, so this part would just reappear here because seeing it as circular, we know how circular, how DFT sees this period, it would see it as circular. Everything you have would just get repeated. So if there is no more samples to put, so it would just reappear from the left. Okay. So this is how you can get D from C. Okay. So this is how you can get D from C. So this is how we get D from C. Also, there is also another way we can get D from B, not B, from A. If you shift A to the left, okay, so you would get something, this part would come here, okay, and this part would reappear here. So this is how you can get back, get D from A. So that one is equivalent to a left shift. And also it seems that it is also equivalent to a right shift. So D seems like it can be obtained by right shifting. Also, it can be obtained by left shifting. Also, it can be, if you do not think of any kind of shifting, if you just think that D was there like this from the start, so it seems like it is also symmetrical around n by 2, right? Same shape to the left and same shape to the right. And if it is symmetrical around n by 2, that means it is actually symmetrical around 0, because if you just take the same thing and connect it backwards, you would 0 would see the same sample to its left, right? So it is also symmetrical around sample 0, so that means it would have 0 phase. So at the same time, it seems like all three phases are correct, because it has right shifting, so that means it would have negative slope, more negative than this. So if it was, if its slope was like this, it would have even more negative slope, because it is even more right shifted. Also, it would be having even higher slope, positive slope than this, because it is even more left shifted from A. And also it can be thought of just being like this from the start without any kind of shifting. In that case, since it is symmetrical around sample 0, so it would have 0 phase. So all these three phases seem to be applicable for D. Another question is, which one is actually correct? Which phase is actually correct? Okay, so if you think about this question, which phase is actually correct, the answer is that they are all correct, depending on how the pi and 2 pi phase ambiguities are arranged. Okay, so since pi and 2 pi, all of them are basically the same, because any integer multiple of pi will be the same phase. Also, any integer multiple of 2 pi will also be the same phase. So since they actually wrap around, if you think of it in this way, that when we were talking about them in the last part of chapter 7, you'll see that after pi, we wrap back to minus pi, right? Then we can go up to pi and then wrap back to minus pi. Ultimately, the thing is that sine pi is 0, sine 2 pi is also 0, sine 3 pi, 4 pi, all multiples of sine pi is 0, all multiples of sine 2 pi is also 0. If you think of it in that way, you'll know that because of that, we can actually consider that not both, all three of these phases are actually applicable for D. All of them are actually correct. And now we move on to this part. There is the, if the sine wave has a very low frequency in figure 10 for A, you'll see that, okay, so in figure 10 for A, you'll see that this is a sine wave of very low frequency. By very low frequency, we mean that within this period from 0 to n, we have a single oscillation. So this is frequency of 1. Okay, but in B, we can see that this is a high number of oscillations from 0 to 32. So in these two cases, we'll have different kinds of result from one sample shift. So the basic thing that is being told here is that shifting one sample to the right will have different effects for these two signals. Okay, one having low frequency, if you shift this one sample to the right, it would be equivalent to 1 by 32, changing the cycle by 1 by 32. But if you shift this one sample to the right, it would be a large change in the cycle. It would be almost equivalent to a half cycle change. Okay, so this is what is being said in this part. So the sine wave that has a very low frequency, for that sample, for that signal, a one sample shift is only a small fraction of a full cycle. But in the other signal, for this signal, the sinusoid has a frequency of 1/2 of the sampling rate. Okay, so this is the highest sampling rate possible, the highest frequency that is possible. For this signal, a one sample shift to the right would be equivalent to an entire half cycle or pi radian shift. Okay, so the basic idea is that the phase is not changed by the same amount for both cases. So that is why we are saying that in the previous part, before the characteristics of the phase, we had said that it is not shift invariant, that the Fourier transform is linear, but it is not shift invariant. Why? So this is the proof of it, that by shift invariant, we would mean that if you perform xn minus k or xn plus k, whatever you did, the corresponding frequency domain would also be shifted by equal amount, right? But that does not happen. So this is the proof of it, that if you think about the phase is not shifted by equal amount. the phase is shifted by shifted proportionally, not by equal amount. If you shift by k for this one, it would get its corresponding phase would get shifted by a very small amount. But if you shift this signal by a k amount to the right or left, its corresponding phase would get shifted by a large amount. Okay, it's the slope will be larger for this one. The corresponding slope would be smaller for this one. So this is the basic takeaway, that when a shift is expressed in terms of a phase change, it becomes proportional to the frequency of the sinusoid being shifted. So the shift is not equal. So that is why it is not shift invariant. Okay, so now we come to this example where in figure 10.5b, this one shows a nonlinear phase. Okay, so as you can see, this one is a linear phase of different signals. One is for the, if it is a zero phase for this line, the zero phase line, you can think of the corresponding time domain signal must have been symmetrical around sample zero. This one must have been shifted. This one must have been symmetrical, but must have been shifted, not around sample zero. It is shifted to the left, and this one is shifted to the right. Originally, whatever the signal was, it was symmetrical around sample zero, but now it is shifted to the right. So that is why it has negative slope. So in this way, all these different slopes correspond to different amounts of shifts to the right and left. But this particular phase means that it was not exactly symmetrical around sample zero. Since it was not symmetrical, so that's why this is a non-linear phase, something like this. There are pulses, maybe like this, or probably it could have been a smooth pulse like this. Whatever it was, any kind of non-linear phase means that originally that signal was not symmetrical, its shape was not symmetrical. Okay, so now this was just an example of a non-linear phase, and this can also react to shifting in the same way. Okay, so any kind of shifting would increase or decrease the slope. Also for a nonlinear phase that was not symmetrical around sample zero, it can also be shifted by, if you left shift it, then it's uh, yeah, if you left shift it, then it's what's it called, the slope would increase. So if you increase the slope, notice that only the slope is getting increased, the shape of the phase is not changing. The nonlinear characteristics of the phase, that means these particular pulse structures, or whether if it was something like this, those pulse structures would remain, only the slope would get changed. So this is what is being said here, that the nonlinear phases also react in the same way to shifting. The nonlinear phase is a straight line with two rectangular pulses in this case. When the time domain is shifted, the nonlinear features are simply superimposed on the changing slope. The slope will get changed in the same way as I've said before for the other linear ones. It will also get changed in the same way linearly. Only the nonlinear features would get superimposed here. So those structures would remain in the same locations, but the slope will get changed linearly. So now figure 10.6, this one shows an interesting demonstration of information, of what kind of information is contained in the phase and what kind of information is contained in the magnitude. So all of this time we have been talking about only the phase part. So now why are we talking about the phase and not the magnitude? That is because most of the information, shift related information and edge related information is actually coming from the phase, not the amplitude. So here an example is shown for this. So refer to figure 10, we'll be referring to this figure 10.6 for this particular discussion. So here, notice that the time domain signal is just a signal that has an edge, a positive edge at around sample a bit before 64. It has a positive edge, and it has a negative edge, that means from high to low a bit before 128. Okay. Uh, okay, and these edges, okay, so here they are saying that it is around sample 55, a positive edge, and a falling edge at around sample 110. Okay, at around 110 we have a falling edge. So edges are actually very important because they actually contain information encoded that are encoded in the shape of a waveform. An edge so what can we understand from an edge? Seeing the shape of a waveform, what can we understand? Wherever we find edges, they actually indicate something happened there. dividing whatever is on the left from whatever is on the right. So maybe this edge could signify something like there was nothing there and suddenly some value came at this particular time interval. We can consider it something like this. Then the value gradually got increased and then the value stopped coming. So a pulse like this gives some information like this, that there was no information being sent, then suddenly there was a burst of bits being sent at this particular time, and these bursts of bits got sent increasingly up to this point, and then there was no bits being sent after this particular time. So these edge locations can give us information like this when the information got started being sent. This is just a kind of networking perspective. Suppose we are applying this thing in case of a networking domain. So this edge, we can see that these edges contain information. Now these edges can be, the location of these edges cannot be found from the magnitude. This can be found from the phase. Now why is that? So now refer to this particular figure. This one was recreated from only the magnitude while discarding the phase. By discarding, we mean we replaced the phase values by uh, random numbers. Okay, so to begin the demonstration of the usefulness of magnitude and phase, they actually performed this experiment such that they took the DFT of the signal in A. Okay, so they perform DFT on this, and then they have the magnitude, both the magnitude and the phase, by converting to the polar notation. Now they got back this B signal. They got this back by changing the phase with random numbers between minus pi and pi, but they kept the magnitude as it was, the actual magnitude as it was, and then they performed inverse DFT on it. So here what happened is they took the actual magnitude, but they replaced the phase with random numbers, and then they performed inverse DFT. So they got back this signal, which is nowhere close to this particular signal. Okay, so this one contains no information about this, as you can see, because this was obtained only from the magnitude. So only taking the magnitude gives you something like this, which is nothing close to this signal. But the other one, for C, this C was generated using the phase information and not the magnitude. So in a similar manner, C is found by replacing the magnitude with small random numbers before using the inverse DFT. Here what they did is they changed the magnitude but not the phase. The phase was kept, the actual phase values were kept. So this makes the reconstruction of C based solely on the information contained in the phase. So this one came from the phase and this one came from the magnitude. Okay, so notice that if you take only the phase information and replace the magnitude information with random numbers, we can get some, we still retain some important features. That is, these negative positive spikes remain in those locations where we had the edges. Okay, so just taking the phase values gives us these features in our signal, but just taking the magnitude does not give us any important features. So the locations of the edges, so this particular experiment shows that the locations of the edges are clearly present in C, but totally absent in B. That means the phase information always contains the edge information, but the magnitude does not contain the edge information. Okay, so in short, much of the information about the shape of the time domain waveform is contained in the phase rather than the magnitude. So this is the ultimate takeaway of this experiment that we just discussed. Okay, now let us go to this final part of our discussion, that is what we have already said, that left right symmetry, any signal that has left right symmetry towards with around a sample 0 is said to have linear phase. Corresponding linear, the phase would be zero phase. Okay, zero linear. So now the question is, why is it like that? So now figures 10.7 actually provides the answer. This particular figure. The first point here is that every signal that is symmetrical between left and right will have a linear phase. Not necessarily zero, but they're saying that any signal that is symmetrical, not just around some sample 0. If it is symmetrical, then it will have a linear phase, because the nonlinear phase of the left half will cancel the nonlinear phase of the right half. Okay, so basic takeaway is that any signal, suppose this is sample 0, but suppose it is not symmetric around 0, suppose it is symmetric around some other sample, suppose sample n, suppose it is symmetrical around sample n. For such a signal, if you just think, if you take it up to this and you take the phase of it, suppose it is non-linear, something like this, and if you take this one's phase, it would be non-linear like this. Okay, and they correspondingly cancel themselves out. Okay, the corresponding values, the positive and negative values cancel themselves out, and they become a linear phase. Okay, so this is why the phase of any symmetric shaped signal would be linear. And if it is around sample 0, then it would be linear, not just around, it would be not just linear, it would be a horizontal line center that is on 0. Okay, so this is basically what it says. So this particular time domain signal, its corresponding frequency domain would be, the magnitude would be something like this. The phase would be a straight line around that is on 0. And if we convert it, if we decompose it, this particular signal in this way, we can have two components. One in this way, where we have this particular part to remain as it is, and the right half is set to 0. We can have a decomposition like this, and this is also the other decomposition component, where we have the right part preserved and the left part is set to 0. So we can, if we just consider this as a signal itself, we can have its magnitude like this. Its magnitude would be half of this, but its corresponding phase would be obviously non-linear, because it is not symmetrical. This was symmetrical, but this is not symmetrical, so its corresponding phase would be non-linear. It would be something like this. Now if we think of the other component, this is also non-symmetrical, so its phase would also be non-linear like this. But if you add them back to get this particular original time domain signal, that this one is symmetric. So notice that if you add these two phases, these two phases are also actually mirror images of each other. One is in the negative direction, or other is in the positive direction. If you add them up, you would get a linear phase. So this is why we get linear phases for symmetric signals. This is a kind of figurative explanation or diagrammatic explanation for why you would get linear phases for symmetric signals. Because if they were not symmetric, you can see that if they are not symmetric, the phases are non-linear. But if you add them up and they become symmetric, you see that their corresponding phases cancel themselves out. Okay, so imagine flipping B such that it becomes C. Okay, notice that this one can be decomposed to get these two parts. Also, only from this part you can get C just by flipping this one left to right. And this corresponding left to right flip makes the phases get inverted. So all the phase values here that were negative, they got multiplied with -1 and they became positive here. So this is just another takeaway, that is, any kind of left right flip in the time domain actually corresponds to multiplying the phase with -1. Okay, so x minus n, so xn, if you have xn and you convert to x minus n by, so this one corresponds to left right flip, right? We have already talked about this in one of our previous chapters, that x minus n corresponds to a left right flip. So this one in the time domain actually corresponds to multiplying the phase by -1. Okay, so phase becomes inverted. So in the frequency domain, this corresponds to the inversion of the phase. This is the basic takeaway from here. The left right flip in the time domain does nothing to the magnitude, but it changes the sign of every point in the phase. Likewise, changing the sign of the phase in the frequency domain flips the time domain left for right. So you can also get this effect, that is the flip effect, by simply inverting the phase in the frequency domain. You can get this this effect in the time domain. So they can be done vice versa. So changing the sign of the phase is a common enough operation actually, and that is why it has been given its own name and symbol. And we already know about this really, from our intermediate level. We call this complex conjugation. So if you remember from intermediate level mathematics, x plus iy has its corresponding complex conjugate, and that would be x minus iy. That means only changing, inverting the sign of the imaginary component. Okay, so this is the complex conjugate of, they are actually the complex conjugate of each other. and correspondingly, this is in the rectangular notation. Correspondingly, in the polar notation, how would we have the complex conjugate? In the polar notation, magnitude x, if you have magnitude x and phase x, the corresponding complex conjugate would have magnitude x and minus phase. Okay, so whatever the phase was for x, you'd have the negative phase. So that is the complex conjugate. They are the complex conjugates of each other. Okay, so this is basically what is being said here, that, and for the notation part, what we are going to be using is that if xf is a signal, then the corresponding complex conjugate would be represented as x star, and if xf is represented in the polar notation by magnitude x and phase x, x star correspondingly would have the same magnitude but the inverted phase. Okay, and I've already said about this, that in the rectangular notation, the complex conjugate would be simply x would remain, the x would be real and imaginary, the corresponding x star would be real, would the real part would be the same, only the imaginary part would be inverted. Okay, so here they are showing some examples of where this is the last part of our discussion. Okay, so now the final topic is the use of complex conjugate. So where may it be used? So remember that if xn has a Fourier transform of capital X, then x minus n, that means the flipped version of x, would have a Fourier transform of x star f, right? So in other words, flipping the time domain left or right corresponds to changing the sign of the phase or changing the sign of the imaginary part in the frequency domain. As another example, we can think of we can remember the correlation, which can be obtained by the same algorithm as convolution. Only in this case, in case of correlation, what is different from convolution? That is, we do not shift, we do not flip the h, right? In case of convolution, we flip h, but in case of correlation, we perform convolution with h minus n. That means we pre-flip it so that when convolution flips it again, it becomes the original h. Okay, so since we have a flipping operation here, this can be done by in the mathematical form. A convolution bn is actually the convolution operation, while a convolution b minus n is actually correlation. So in the frequency domain, this can be done easily because the corresponding frequency will be multiplied, frequencies will be multiplied, right? So this is equivalent. If you want to perform correlation, we just perform multiplication with the complex conjugate of b. That means if just know that b minus n in the corresponding frequency domain, it would be equivalent to the complex conjugate of capital B, right? So the complex conjugate of capital B can be just multiplied with A, and we would get the correlation operation simply. Now the last example where this complex conjugate, the concept of complex conjugate may be used. Here we can consider that any arbitrary signal xn and its corresponding frequency spectrum capital X. In that case, the frequency spectrum can be changed to zero phase. Okay, so xf, the capital X, this capital X may not be symmetrical around zero. Okay, so capital X, if it is not symmetrical around zero, or the corresponding time domain capital small x, if it is not symmetrical around zero, then its phase will obviously be not linear, not horizontal, right? Even if it is linear, but it may have a positive slope if it is not symmetrical around zero, if it is symmetrical around a different point. So any such signal can actually made to be around symmetrical around zero. That means its phase can be made to zero. How? Simply by multiplying itself with its complex conjugate. Okay, so multiplying any frequency spectrum with its complex conjugate converts any kind of positive slope or negative slope to zero slope. That means its phase can be made to be zero. Why is that? Because if we remember, when you multiply two signals, their magnitudes get multiplied and their phase gets added. So what you're doing is you're adding p with minus p. So what you're doing is you're just making the phase zero. the corresponding phase component would become 0. So that is why you would get phase like this. And in the time domain, this is equivalent to multiplying a signal, convoluting. Since you are multiplying here, so in the time domain it would be convolution. So in the convolution, this is equivalent to convoluting a signal with its flipped version. So if you convolute a signal with its flipped version, you can get the same thing. You can get a signal that would become symmetric around 0.0. Okay, so suppose it was symmetric around a different point before. If you perform this thing, convolution with the flipped version of itself, it would become symmetric around sample 0. So notice that this has a particular use, because this is useful for centering a signal. Okay, so if you have a shifted version of a signal, you can actually center it around sample 0 by doing this operation. In the time domain, you'd have to do this this convolution, and in the frequency domain, you simply have to do this multiplication of itself with its complex conjugate. So this is all about the use of complex conjugate, and we'll be ending our lecture here. In our next lecture, we'll be actually talking about periodic nature of the DFT. For now, we'll be that's all for today. Thank you, everyone.